Have you ever found yourself just, staring out a window on a lazy afternoon, maybe watching a sunbeam cut across the room?
Oh,
You
absolutely.
see those little dust motes floating there, just
No,
just dancing around. They jitter, they swirl, they almost look like they're alive.
it's a universal sight. And if you were to look at, say, pollen grains in water under a microscope, you'd see the exact same thing, that same chaotic, jittery dance.
Right. And for most of my life, I thought I knew what that was. It's Brownian motion. It's the classic, high school physics
It's
example.
a textbook definition.
Yeah, exactly. We're told that these invisible water molecules are zooming around like tiny billiard balls, crashing into the dust or the pollen and kicking them around.
And that's been the standard story for, what, over a century? It goes back to Robert Brown in 1827.
And then Einstein himself stepped in, right, in 1905, with this statistical model that seemed to wrap it all up with a nice bow.
Case closed, or so we thought. The idea was simple. Heat makes molecules move, and those moving molecules push the pollen.
But today, we are reopening that case because we've got a stack of research here from a physicist, Jerry Z. Liu, that claims the math behind that standard story
The one we've all just accepted.
is actually impossible.
It is a very bold claim. The source argues that if you actually sit down and do the momentum calculations, the numbers just, well, they don't add up. The water molecules physically shouldn't be able to push the pollen at all.
So our mission for this deep dive is to unpack this argument. We're going to look at why water molecules might be too weak to push pollen. Then we'll introduce a new mechanism called transimpact.
Which involves, and this is the fun part, exploding atoms.
Exploding atoms, right. And then we'll see how this could rewrite everything from how a simple toy works to what temperature actually means.
It really suggests we've been looking at a shadow this whole time and calling it the object.
Okay, let's start with that impossible math, because when I first read this part of the source, I honestly had to stop and reread it. It felt like someone pointing out a huge plot hole in a movie I've seen 100 times.
It's a matter of, checking the receipt. Let's look at the setup. You have a pollen grain. To us, it's tiny, maybe 50 or 100 microns wide.
But on an atomic scale, it's a giant,
Yeah.
an absolute behemoth.
Exactly. A single water molecule has a mass of about 2.99 times 10 to the minus 26th kilograms. It's just vanishingly small.
Okay.
Now, for us to see that pollen grain move, even a tiny, barely visible wiggle, it needs to reach a speed of roughly 300 nanometers per second.
Which sounds incredibly slow to us, but for something that heavy, I imagine it requires a real shove.
A real shove, exactly. Newton's laws still apply. So the source asks a really simple question. If one water molecule is responsible for that shove, how fast would it need to be going?
And this is where the standard theory just hits a brick wall.
It really does. The calculation shows the water molecule would need to be traveling at 3.21 times 10 to the 7th meters per second.
Whoa, okay, wait, I need some context for that number. Sound travels through water at what, maybe 1,500 meters per second?
Around that, yes. And the average water molecule at room temperature is moving at maybe 590 meters per second.
So we need them to go, 32 million meters per second?
To put it in perspective, that is more than 10% of the speed of light.
That's insane. So for the standard theory to work, for a single water molecule to push a pollen grain, that tiny molecule needs to be moving at relativistic speeds.
Precisely. It is orders of magnitude higher than anything physically possible in liquid water. I mean, if water in your coffee cup was moving that fast, you wouldn't have a beverage. You'd have a high-energy particle accelerator on your desk.
Right, the cup and the desk would be gone.
The whole kitchen, probably.
Okay, so the one molecule theory is out.
Yeah.
But surely, I remember my physics teacher explaining this. It's not one molecule. It's a group effort, a statistical thing.
The rugby scrum idea, right.
Yeah. A bunch of them just happen to hit one side at the same time.
And that is the most common counterargument. It relies on what's called statistical fluctuation. The idea that just by chance, more molecules hit the left side than the right.
A swarm.
But the source anticipates this, and it runs the math on the group effort theory, too, to get that same momentum transfer using normal speed water molecules.
At that 590 meters per second.
Yes. You would need 54,418 molecules to all hit the pollen grain at the exact same moment.
Okay, 54,000, that sounds like a lot, but in a drop of water there are, trillions and trillions. So is that doable?
Well, it's not just about them hitting at the same time. They have to hit the exact same spot from the exact same direction.
Oh. Okay, I see the problem.
Remember, molecular motion is pure chaos. They're moving up, down, left, right, spinning. The probability of over 50,000 of them all coordinating to strike one side of the pollen grain is, well, the source calculates it as 2 to the power of negative 54,418.
Which is effectively zero.
It is so close to zero, it's meaningless. In the entire history of the universe, it would never have happened. Not once. It's statistically impossible.
So we're left with this huge problem. One molecule can't do it because it's way too slow. And a group of molecules can't do it because they can't coordinate. So, why is the pollen moving? I mean, we can all see it move.
And that is the million-dollar question. If the force isn't coming from an external collision, like a billiard ball, then the force has to be generated in a different way.
Which brings us to the core concept of this research.
Transimpact.
Transimpact. It sounds like something out of science fiction. A new warp drive.
It stands for transition impact. And to understand it, we have to stop thinking of molecules as hard little balls and start looking inside the atom itself.
Okay, let's unpack this. Take us inside the atom.
So we all know atoms have a nucleus and electrons orbiting them. And when an atom absorbs energy, say from heat or light, those electrons get excited.
They jump up a level. I remember the Bohr model, the little energy shells.
Right, they jump to a higher orbital. But here's a physical reality of that jump that usually gets glossed over. When that happens, the atom gets bigger.
How much bigger? Are we talking like a tiny fraction of...
No, a massive expansion. The source uses oxygen as an example, since we're talking about water. In its ground state, an oxygen atom has a radius of about 48 picometers.
Okay.
But when it gets excited, that radius can jump to 118 picometers.
That's more than double the width.
And in terms of volume, it's an increase of over 1,200%. And this happens in nanoseconds.
Whoa. Okay, so it's like you're in a crowded elevator, shoulder to shoulder, and suddenly the guy next to you instantly puffs up to 10 times his size.
That is the perfect analogy. It's a spacing issue. The source actually uses the analogy of popcorn.
Popcorn, I love that. It's so simple.
It is. Think of a water molecule right next to the pollen grain, like an unpopped kernel. It absorbs a little thermal energy. And then pop.
The electron jumps, the atom expands.
Explosively. It's not just bumping into the pollen. It is forcefully shoving it away because it physically needs that space now.
That is such a vivid image. So it's not a game of billiards with things knocking into each other. It's more like a minefield of little popcorn explosions going off constantly.
That's the theory of transimpact. The force isn't from kinetic momentum transfer. It's a repulsive force from the sudden, violent expansion of the electron clouds. That pop gives the pollen the kick we see as Brownian motion.
It just makes so much more intuitive sense than the rugby scrum idea. You don't need 54,000 molecules to agree to move left. You just need the one right next to the pollen to pop.
Exactly. It turns the motion from a statistical miracle into a mechanical inevitability. And this mechanism, it doesn't just explain dancing pollen. The source argues it solves another mystery that's been bugging physicists for a century. The Crookes radiometer.
Oh, I know these. The little glass bulbs with the spinning windmill thing inside. The vanes are black on one side, white on the other.
Yep, you put them in the sun and they spin like crazy.
And do you know why they spin? I always thought it was the light pushing them, like a tiny solar sail.
That's what a lot of people think, but the actual pressure from photons hitting the surface, it's nowhere near strong enough to spin them that fast.
Okay, so then it has to be heat. The black side gets hotter than the white side.
That is the prevailing theory. It says the black side absorbs light, heats the air molecules next to it, and those hot air molecules bounce off harder, creating a pressure difference.
Which pushes the vane. Sounds reasonable, so what's the problem with that?
The problem is the timing. Thermal processes, like heating up air, they're slow, they take time.
There should be a lag.
There should be a lag. You turn on the light, the vane heats up, the air heats up, pressure builds. The spinning should start slow and ramp up like a steam engine.
Right. But that's not what happens.
Not at all. The source presents experimental data that shows something completely different. When you shine a light on the radiometer, the acceleration is at its maximum immediately, at time 0.
It's instant, no lag.
Instant, there's no ramp up. And the old thermal pressure theory just cannot explain that. If you put a pot of water on the stoves, it doesn't boil instantly. But transimpact can explain it.
Because of the electrons jumping?
Precisely. Light hits the black side. The atoms on that surface absorb the photons instantly. Their electrons jump to higher orbitals. Pop, pop. The atoms expand, creating that explosive repulsive force against the air molecules. It kicks the vane immediately.
So it's basically an atomic engine. The light is the fuel, the electrons are the pistons, and transimpact is the combustion stroke.
That is a brilliant way to put it. The deceleration comes later as air resistance builds up. But that initial instant start is the smoking gun for transimpact.
This is fascinating.
Ah.
But the source goes even further, right? It starts to attack our actual definition of temperature itself. And this is where my mind started to bend a little.
This is where the deep dive gets really deep. We're all taught that temperature is a measure of the average kinetic energy of molecules. Basically, how fast are they jiggling?
Hotter equals faster. That's physics 101. If I heat up a gas, the molecules fly around faster.
The source calls this a misconception, even a delusion.
Strong words.
Very strong. But the evidence lies in something called specific heat.
Okay, remind us what specific heat is again.
It's the amount of heat energy you need to add to something to raise its temperature by 1 degree. So if temperature is just speed, kinetic theory should be able to predict exactly how much energy you need to make molecules speed up.
It's a simple budget calculation. I put this much energy in, I get this much speed out. Does it work?
For very simple monatomic gases like helium, yes, it works great. A helium atom is just a single ball. You push it, it moves faster.
But for more complex stuff?
As soon as you get to complex molecules, what they call polyatomic molecules, the theory just falls apart completely.
How badly does it fall apart?
Let's take octane, the stuff in gasoline. It's a big, complex molecule. Standard kinetic theory predicts a specific heat for octane, but when you actually measure it in a lab, the prediction is off by 93%.
Wait, 93%? That's not a margin of error? That's just being wrong.
It means the theory only accounts for about 7% of where the energy is actually going. The other 93% is going somewhere else.
That's a staggering gap. So where is all that energy going, if not into making the molecule fly faster?
Into potential energy. The source argues that those chemical bonds inside the molecule act like springs. When you heat up octane, you aren't just making the whole molecule move faster, you are stretching all those internal springs. You're exciting electrons into those higher, puffy orbitals we talked about.
So the energy is being stored inside the molecule's structure, not just in its motion.
Exactly. And the source argues that temperature is actually a measure of this thermal energy, which is mostly potential energy, not just the kinetic side effect.
This brings back to the popcorn idea. The energy goes into loading the spring, into expanding the atom until it pops. The motion, the kinetic energy, is just stuff flying away after the pop.
Yes. The source literally says kinetic energy is a shadow of potential energy exchanges. We've been measuring the shadow this whole time and thinking it's the real object.
This actually explains the final puzzle piece, right? Phase transitions. I remember being so confused by this in school. You take a block of ice at 0 degrees Celsius, you put a flame under it, and while it's melting, the temperature stays exactly at 0.
Right. You're pouring heat in, the flame is hot, but the thermometer is stuck.
If temperature's just average speed, shouldn't the water molecules be speeding up as they break free from the ice? Why doesn't the temp rise?
Under the standard theory, it's a bit of a paradox. They say the energy is used for breaking bonds, so it doesn't count as kinetic energy. But it feels like a patch on the theory.
So how does transimpact explain the flatline thermometer?
Think of the hydrogen bonds holding the ice crystal together. They have a limit to how much potential energy they can hold, how much they can stretch. The source says the temperature is anchored by this limit.
Anchored. I like that word.
As you add heat, you are stretching those bonds, increasing their potential energy. But you can't go above the bond's limit. When a bond stretches too far, transimpact occurs. The repulsive force pops, and the bond breaks.
So the phase change happens.
The phase change happens, but because the level of that potential energy state is capped by the strength of those bonds, the temperature literally cannot rise until all the bonds are broken and the phase change is complete.
So the thermometer isn't measuring speed. It's measuring the tension in the springs. And once the spring snaps, you can't add any more tension to it.
Exactly. It completely reframes what we see on a thermometer. We're not measuring speed, we're measuring the emission level of the system's potential energy.
Wow. This is a lot to take in. I mean, think about the journey we just went on. We started with pollen dancing in water, which turned out to be mathematically impossible under the old rules.
Impossible speeds, impossible coordination, it just didn't work.
Right. Then we moved to these exploding atoms, the popcorn effect, driving everything from that pollen to the spinning vanes of a radiometer.
Proving that the force is instantaneous, not slow and thermal.
And finally, we realized that our entire concept of heat and temperature might be backwards. That kinetic energy is just the exhaust, and potential energy is the fuel.
It connects all these disparate dots in a really unique way. It suggests that transimpact, this physical expansion of electron orbits, is a fundamental engine of the universe. It's the mechanism that converts stored potential energy into kinetic energy, into motion.
It's weirdly beautiful, actually. It makes the universe feel less like a sterile pool table with balls banging around and more like almost a living, breathing thing.
Yeah.
Expanding, contracting, popping, pushing.
It restores a certain mechanical causality to physics that was sort of lost in pure statistics. Instead of just saying it's random motion, we can point to a specific mechanism. The electron jump, the pop.
So what does this all mean for you listening? Next time you boil a kettle or watch dust floating in a sunbeam, just remember. You might not be seeing things bumping into each other. You might be seeing billions of tiny quantum explosions, atomic popcorn popping constantly to drive the motion of the world.
And it leaves us with a pretty provocative thought. If kinetic energy is just a side effect, a symptom of these potential energy exchanges, how many other fundamental laws of thermodynamics might be based on correlations rather than true causation?
Are our thermometers even measuring what we think they're measuring? Are we all just looking at the shadow on the wall?
Yeah.
That is something to let simmer. Thanks for diving deep with us today.
It was a pleasure.